Good morning, student. Okay, it's our the 15th week of this class. Okay, decision science for security, cybersecurity. Okay, let's take a look at this week's schedule. It's right here. We are about to finish off our analysis algorithms and neural network. Okay, today we will go over some brief introduction to intrusion detection. So, but this hour, I will try to finish some unfinished slide and some notice about neural network and machine learning algorithm. Okay, so let's start. The first thing we'd like to talk about is this specific figure. Okay, you can download this figure from my Google Drive. Okay, the name is called sensitivity. Okay, it may take some time. Okay, in this figure, okay, it's provided by someone else. Okay, I downloaded from network. It's called sensitivity of model to some hyperparameters. Okay, when we try to analyze some data, okay, try to solve a problem, okay, I think neural network is one of the way you model the data. Okay, you have a model and try to construct a relationship between the input value and the output you target. Okay, so you will try to construct a neural network. Okay, as a designer, okay, I mean neural network structure designer, you have to decide, okay, what kind of model you would like to use. I mean, how many layers you would like to use, and in each layer, what kind of layer, for example, it's a dense layer, or it is a convolution layer, or it is a max pooling layer you would like to use. And in each layer, there are several we call hyperparameters, which means how many neurons you would like to use, what kind of optimizer you would like to use. There are some other parameters. Okay, what is the learning rate you want to apply in your optimizer? So there are several different parameters you may choose. Okay, as a designer, you have to choose what kind of parameters, what's the value you want to use, because those value deeply influence the effectiveness and the efficiency of your model. So here's a list of hyperparameters. For example, learning rate schedule, loss function. Okay, the right hand side is the sensitivity, which means if you try to fine tune those hyperparameters and how sensitive, okay, those hyperparameter is. If you change this value with high sensitivity, that means your model changes a lot. So you can more quickly, I use the word quickly, okay, you can more quickly to tune your model to fit your data. However, as we mentioned before, sometimes we have some problem called overfitting or underfitting. That means you don't have to tweak your model so quickly, because sometimes your model will too aggressive, which I mean, if your model is too aggressively to do fine-tune work, the model will remember, I use the word, okay, remember, the model will remember the data you use and try to memorize what is its output. Okay, I will draw a figure afterward. Okay, that is not a good situation you would like to encounter, because your model would prefer remember the answer, not to really build the relationship between X and Y, your input and output. So your model, when you do testing or you do validation, okay, your model would be a little bit, we say overfitted. So here is a list. Okay, so if you have a model, okay, no matter what it is, it's a convolution or it's just a very simple dense neural network. If your model does not perform quite well, okay, try to modify those hyperparameters from the top side. Okay, learning rate. You can change the learning rate. For example, the learning rate we mentioned here is the initial learning rate. In our previous lecture, we have explained some different optimizer. Those optimizers will change your learning rate. Okay, when you do the training. So, for example, some add-on optimizer, ADA optimizer, they have some different concept like momentum, like change the learning rate. So the learning rate we right here is the initial learning rate. If your initial learning rate is too large, that means you can explore your loss function surface, but it might not be able to find the lowest loss function value. That's because your learning rate is too large. So your span every time when you do partial differentiation, okay, you might not you have a right direction, but as we mentioned before, sometimes it's not possible to find the lowest loss function, that point data lowest loss function value, because the learning rate is too large. Okay, that means you every time you change your span, your direction, okay, you can it's not that fine granted. Okay, so sometimes you need a small learning rate, but usually at the end of your training. So if you encounter some situation like every time when you train your neural network and you observe that the loss of the loss value, it seems like it does not decreased very aggressive, you can try to increase your learning rate at the beginning of your training. So as the initial value of your training, it might be able to push your loss function value to a much lower point at the beginning of your training. So learning rate is the most sensitive hyperparameter. We can try to fine-tune it. And the second one is the learning rate schedule. It is related to the optimizer you use, because sometimes your optimizer, as we mentioned before, your optimizer will use the initial learning rate, okay, as its initial learning rate, but it will change the learning rate. So sometimes you need a very large learning rate at the first beginning of your training, and you need a very small. Okay, conceptually, you need a small learning rate at the end of your training, so that you can explore your loss function surface at the first place, and at the end of your training, you can find the lowest loss function value. Okay, so that is the learning rate schedule. Loss function, usually, again, as we mentioned before, if it is a regression problem, okay, so your target value y, it is a numeric value. Usually we use MSE or square root of MSE. That is good enough. Usually we do as a general problem, okay, a general ordinary regression problem, we don't use some other loss function, which is so MSE or is good enough. Okay, for the classification problem, okay, usually we use cross entropy, or we use sparse cross entropy. You can check them out in the Keras API. So you can most time cross entropy is good enough. But for some application, if you want some very specific loss function, which is good enough, which is good, because if you know your y, they need to fit some distribution. They need to you want to improve it rather than use regression, which means you rather than use MSE or cross entropy, you can design your own loss function. At Keras, indeed, it's it has a function that you can customize your loss function. And again, we mentioned it before. Sometimes when you use the cross entropy, or sometimes you use MSE, try to apply regularization as well. Okay, we talked about last week. When you apply regularization, no matter it's a L1 regularization, L2 regularization, okay, or you say it's a lasso or regularization, that can help you to do feature selection and to do to prevent overfitting as well at the same time. Okay, the next level is units per layer, which means how many neurons you choose to use in each layer, and number of layers. Okay, the third one is number of layers. Okay, they are not that as sensitive as the hyperparameter of learning rate and loss function, because they help you to find the lowest loss function value. The second one, most of them are related to network structure. Okay, how many layers you want to use, how many neurons you want to use in a layer. As we mentioned before in the last week, I think this is the most important topic to talk about. Those activation function, those neurons, those layers, they are simply just some way to push or twist your original space to another new linear space. Okay, I think we mentioned it in the last week. So those things are very important. So how many times you want to fold your original space, and how many times you want to you create a boundary line, how many boundary line you want to create in your original space. So try to modify them if you think the learning rate and loss function is good enough, and you think that the performance of your neural network is not good enough. So you can try to fold your original space. Okay, so that is, and the second one is the parameter initialization strategy. Okay, we I think we haven't discussed it this strategy. Okay, as we mentioned before, when we do for example regression, use a neural network to do a regression problem. Okay, and I think you can draw a graph. Okay, I think we draw it a lot of time. Okay, we have a function like this, right? But we don't know this value, this weight, a and b. Okay, something like that. Okay, so if we do MSE, okay, this question we write it a lot of time, right? So we will have a value like this, right? This is A, this is B, and this is MSE value. Okay, and or sometimes we can draw it in this way. That is A and that is B, and we can draw some figure like this. Okay, that is MSE value. Okay, for example, it is a hill, so it is a higher place, and then okay, it disappears. So that's okay. We can draw it again. Okay. Okay, so it is a basin. Okay, that is a basin. So that is a higher place, and that is a lower place, right? So basically, at the first place, okay, when we do gradient descent, okay, we simply just select a random value of a and b. Okay, so here theta is a and b. Okay, theta 0. Okay, t is theta. Okay, t is 0. So we simply just random select an A and B and see how it performs, okay, based on the value of MSE value, okay, that is MSE Bayesian, okay. So by partial differentiation, it tells us how where is the direction of A and B, okay. Maybe A says, okay, if you do partial differentiation on X, okay, so it knows, okay, A should go this way and B should go this way, so that we can have a lower MSE value. So basically we go this way, right? However, that is the first data point we choose, which is theta t equals to 0. So at the second data point, maybe it's right here, right? So that is theta. Okay, the second theta, the better theta, after we do partial differentiation. So here we're talking about right here. That is the parameter initialization strategy, which means at the first beginning we said you can simply just randomly choose initial value of your A and B and try to do to do your gradient descent to find the next theta, next. So you will get the optimized theta. So, but sometimes, okay, choosing the initial value might be important for you. But however, in Keras or in TensorFlow, sometimes we just simply use the simplest strategy to select our strategy. Okay, those strategy used in I think that is some synchronization problem. Oh, this one. Okay, so that's okay. So sometimes when we choose different initial parameter of A and B, okay, those weight, usually, okay, I say usually we use a random strategy, which is okay, but sometimes in Keras or in TensorFlow, okay, they have a specific strategy, okay, that is again, we have A and B, okay, we have MSE value right here, okay, so theta 0, that is the first data point we choose, okay. Of course, oops, I think that is the synchronization problem, because it is synced by some other device that I use. So I like to choose a new, okay, this one. I think that will be much better. Okay, so most of the time we have a lot of, most of the time our weight will be like this, all right? Okay, so for this weight, okay, it can be a very like, for example, it's a 300 dimension. It's a 300 dimension weight, right? We start from grade 0. So we have too many weights. So basically, we have to choose a lot of random values as their initial values, so that we can do partial differentiation. So I think most of the time when we do randomly choose some parameters, usually, okay, I say usually, okay, TensorFlow or Keras, okay, they simply just have a normal, sorry, they have a normal distribution, okay, so they can simply use a very simple normal distribution, which is mean value is 0 and their standard deviation is 1.0. Okay, so that is 1.0, and they those very nice function. They help you to randomly select values and use those values as those initial values. Okay, so that is one of the strategy you can set those values. So the value you use right here, W0 to W299, their initial values comes from a very simple normal distribution, which is mean is 0 and its standard deviation is 1.0. So on the average, we say on the average, okay, half of the weight, okay, I mean initial, half of the initial weights, they are less than 0, which means they are negative numbers. And half of the weights, they are positive numbers. Okay, they're positive numbers. And lots of weights, their initial value are 0 because the mean value of this specific normal distribution is zeros. Okay, but after that, when we do the first partial deviation, those values will be changed, right? Will toward the direction of lower loss function value, lower MSE value, right? So if sometimes you think why I have a proper let's go back to here. For example, I have a proper learning rate and have a proper number of units in each layer, number of layers, and have a very common loss function, something like that. But it seems like my model does not move, which means every time I do partial deviation, those weights, it seems like they do not move quite obviously. So maybe that is a time you would like to change such kind of strategy, initial weight strategy. Okay, you have to think about it. Half of your weights are currently negative number, half of the weights are positive number, and some of the weights are zeros. Zeros means, which means some of your axis right here, right? So that means, okay, x1, x2, x0, x299. Okay. Some of the weights initially, okay, they do not pass any information from the input to the right hand side, or some of the initial weights, they are quite close to 0. Right? Because your weight is randomly choose from a normal distribution, so a lot of data, a lot of randomly choose weights will be close to close to 0. So maybe that is one of the reasons that initially your information, which is your x0 to x299, does not pass to the right hand side. So that the partial deviation does not did its job. So sometimes you can, you can choose some other way to initialize your strategy. Okay, you can check them out in Keras. Okay, there are several different ways to initialize your initialize your weight. So that is the parameter initialization strategy. Okay, they're related to how your neural network looks like at the first beginning. Okay, but as I mentioned, even if you don't choose different strategy of parameter initialization, okay, if your learning rate and if your optimizer is good enough, okay, they will gradually change those weight. Although the speed of changing those weight would be a little bit slower, but eventually they will find the direction of the lowest loss function value. So basically you get your result a little bit slower if you choose the wrong parameter initialization strategy, but usually usually you still can get the right answer. Okay, but a little bit lower, a little bit slower, okay. So that is the second part. Okay, the next part is the layer properties the degree of regularization choose a parameter. Okay, layer property, that means if you use different kind of layers, such as convolution, such as dense functions, such as max pooling, there are a lot of different layers provided by Keras, but we only mention some basic ones. So different kind of layers, okay, they indeed has different sensitivity. Okay, degree of regularization, which is L1 regularization and L2 regularization. Okay, choose the parameters we also talked about before. Okay, so that's the second. This is the third part. The last one, optimize the parameters, size of mini batch, choose of a linearity. Okay, so that is the, I think, the last sensitive ones. Okay, the size of mini batch. That means every time when you do partial differentiation, how many data you would like to use in your training data to do each run. I mean each run or each epoch. Okay. If you have, okay, you can draw it again. Okay. For example, if you have a lot of different data, right? Okay, you can simply choose part of the data, okay, and you apply those data in your MSE. Okay, suppose let's just assume it is a regression problem. Okay, you can choose part of data, okay, when you do training, okay, and you calculate the next weight, okay, by using part of data. Okay, that is what we call mini batch. Okay, the next time when you fine-tune your weights, okay, next time you can use another part of your data to do next time training, and so on and so forth, so on and so forth. And of course, okay, for example, if we divided our data into 3 different mini batch, and you can do partial differentiation each time, okay, by using one of the data set. Okay, so of course you can repeatedly, okay, use these 3 different mini batch. Okay, for example, you can train your neural network, for example, 300 times. Okay, 300 times, and each time you use different data set. So so at the end of your training, okay, we say mini data set, okay, mini data set, they are trained 100 times because you trained it 300 times in total, and each time you use different mini data set, so each mini set has been trained 100 times. Okay, that is one of the strategy you use. Of course, you could train the data set, for example, 3,000 times. So each mini data set will be trained 1,000 times. But that might not be a good strategy because you train those data set too many times. So it might encounter some overfit situation. Okay, we will talk about overfit and underfit later. Okay, again. So you have to select proper times to do such kind of training. Okay, how many times you want to do the training, and of course there are some other strategy. For example, okay, you have 300 times training process you have to do. So the first time you use this data set, the second time you use one, and the third time you use one. Okay, and at the 4th time you do the training, you can simply just again use the first mini data set. That is okay, but sometimes, okay, if you think you want to make your model more robust, okay, you can at the 4th time you can sort or random, usually randomly. Okay, you can randomly shuffle this data set. Okay, and in this shuffle data set, you can again partition this dataset into 3 different mini datasets, and at the 4th training, okay, you use one of the dataset after shuffling. Okay, so that each time you can, that is one of the way you try to improve your model. Okay, that is one of the way. Again, you can choose different strategy of every time you do the training. Okay, so you can random, after you use all of your data set, you can randomly shuffle it, okay, to create a new different orders. I mean different orders, and use different orders to partition your data again, and do the training again and again. And every time you run out of your data set, you do the shuffle again. Okay, that is one of the way to have different strategy. Okay, and of course you can change the size. For example, you partition your data into 3 different mini set, 4, 5, 6, 7. It all depends on you, and how many times you like to go through all your data set, which is right here, the size of the match. Okay, how many batch you like to do? 1,000 times, 100 times. Okay, we'll talk about it later. Okay, the choose of non-linearity, which means the activation function you choose. Okay, in the previous class, okay, we talked about activation function, right? Activation function. Different activation function will tweak or push or twist your original space to a new landing space, right? So basically they present different non-linear relationship between your layers of your neural network. Okay, so that is okay. So basically, I think that is okay. This figure, I think this when you try to fine-tune your neural network, okay, try to, if your neural network does not perform good, okay, try to modify your neural network from the learning rate, rate scheduling, loss function, and to the end of this list. Okay, I think that would be helpful. Okay, so that's it. That is what I'm talking about right here. Okay, so I'd like to take some time. Okay, we have 15 minutes, right? So I'll take some time to talk more about our one of our homework. Okay, I think that's a little bit important. So that is the homework number 4, I believe. Okay, so I think that is right here, number 4. Okay, I'd like to explain something more about the PE file and how do we use convolution neural network to analyze these PE files. So that's right here. Okay. So I think we can change it to it. Okay, I think that's good. Okay, so that is right here. Our homework number 4 is here. Okay, PE file and the convolution neural network. So here is it. Okay, as we mentioned before, PE files, it is a file, right? It has several different headers, several different payloads, several different sections to store the information about a program. Okay, so basically we have a very simple idea is that, okay, different programs, I mean, no matter it's written in Java or written in C, no matter what it is, if you want to deliver your malicious software, okay, to some other victims, okay, you have to compile it into a PE file. Okay, basically the target is Windows system. Okay, so the PE file looks like this. However, in the PE files, different sections, they represent the different codes you've written. I mean the attackers written. So basically, okay, I give you some example right here, right? So basically, you read those files, okay? And firstly, okay, we have 356 PE files which I provided to you, okay? And for each malicious software, okay, I simply just extract the first few bytes, okay, and I form them in a 28 by 28 matrix, and each element in the matrix is a byte extracted from the malware. Okay, so that is so. Here also we have the answer, which is our target. Okay, as I mentioned before, we have. I think it's right. I think it's right here. Okay, it's right here. Of course, I know the answer because I create this data set. Okay, there are 11 different malware families, which means for each family, okay, we strongly believe that some malware, they are created by specific hackers or specific groups. Okay, so they simply just use their old code, okay, and to modify them and to create a new variant. Variant 就是变种的意思 to create a new variant of this malware family. Okay, so among these 356 malware samples I provided to you, they belongs to 11 different malware families. Okay, so that is the answer right here. Okay, so the 5 right here means the first malware I provided belongs to the 5th malware family. So let's start from 0. 0, 1, 2, 3, 4, 5. Okay, so the first malware belongs to Buta-RFN, okay, which I don't know what this means, but it is the name of this malware family. Okay, so that is. So let's take a look at the first sample. Okay, as I mentioned, it is a 28 by 28 matrix. Okay, and in this matrix, okay, each element is an integer. It represents the bytes, okay, extracted from the PE file. So that is the first 28 byte extracted from the PE file. Okay, it says 77. That means the first byte is value. Okay, if we represent it in as we know, each byte has 8 bits, right? So we can use a value to represent this byte. Okay, between 0 and 255, right? So the first byte is represented as 77 if you use a decimal system to represent this byte. Okay, so that is the first 28 byte, that is the second 28 byte, and so on and so forth. So we have 28 by 28. Okay, and that is a very special analysis. Okay, so that means if I draw this 28 by 28 matrix by using different colors, okay, so here is the matrix. Okay, start from the left top side. Okay, that is the first byte, second byte. For each row we have 28 bytes, so we have 28 rows. Okay, so the color right here. Okay, so I use a very simple function called imShow. That is image show, and the image show, it has its input parameter is our first malware sample. Okay, so basically it's a 28 by 28 array. So basically it will draw a figure like this. Okay, of course you can choose your own color. Okay, but in here, in this example, the value of each byte, each item in the matrix, if it is close to 0, it will be darker, a blue in blue color. If it is close to 155, okay, then it will be close to yellow and some colors right here. Okay, so basically we originally it is data, okay, which can be viewed as a representation of a bytes value. So here we simply just we simply just think, okay, we can represent it as an image, and for each image, okay, we can use a color to represent its original value. So we can see that here is a pattern, right? Because the human eyes, human brains is very powerful. So we can see that, okay, there are some patterns right here, even if they are simply just some random bytes or there are some codes in your original PE files. But you know, human brains are incredible. We see, okay, there's some patterns right here. Okay, there's some yellow dots right here. There's some green dots right here. Although we don't exactly know what it represents, but you know, there are several researchers have proved that such kind of representation truly can represent the data, and those images can truly analyzed by CNN or by any other neural network. So sometimes, okay, even though we don't have we don't know what exactly the data represent, okay, that there's one concept, okay, you have to remember that. If we can represent those data by using an image, no matter this image is meaningful or meaningless to our brain, but we can use a convolution neural network or neural network to analyze it. Okay, so let's take some example right here. Okay, I draw this figure for you. Okay, so I randomly pick some samples from our 365 samples. Okay, so I plot it in this way. Okay, I plot all of their 28 by 28 bytes. Okay, but here I just for simplicity, okay, I use a grayscale figure right here. Okay, so let's take a look of these patterns. It is incredible that, for example, we can take a look at the last three images right here. Okay, originally they are simply just bytes in the PE files, but if you draw a figure for them like this, you can say that, okay, it seems like the ferret family. Okay, there are three variants, three samples of this variant. Okay, at the first beginning, their bytes, the bytes they used in the very first in the first few bytes. Okay, it seems like there is a straight line right here. Okay, straight line. They are gray. They are in gray, and there are several. Okay, I can make it bigger. Okay. It seems like there are 1 dot right here and 3 dots right here and 1 darker dots right here. So the 1 dots, 3 dots, and 1 dot, 1 dot, 3 dots, and 1 another dots right here. Okay, let's go back to here. Compared to Z-bot. Okay, compared to Z-bot, there are still some dots right here, but it just seems like those dots are not. You can see that the first dot right here is a little bit far away from the second dot, but in Z-bot, this dot right here is a bit closer, right? So it seems like it's truly that some patterns exist in this PE files. Okay, and we can see that for example again, for this ferret, okay, there's there's a diagonal line. Okay, there's a line right here, and in this line there's a dot right here. You can see that. Okay, the other variant, okay, its dot is it has two dots right here, but there is still a diagonal line right here. And for this another variant which is also belong to ferret, it seems like this line exists. But however, if you take a look at other mirror samples, it seems like most of the other variant in other mirror family, they do not exist such kind of patterns. And if we use convolution neural network, we can find such kind of pattern in ferret family. Okay, so sometimes of course not all the patterns of ferret family does exist such kind of diagonal line, but we believe, okay, it might be helpful for us to find them, to classify them. Okay, so for example, there's another family called hot bar, and you can see the first few bytes right here is not like ferret, right? It's more darker, more dots right here, like this one. Okay, so there's another hot bar, there's another hot bar. Okay, and the first few bytes, they look much darker, right? So that is the concept. So if you observe that your data truly has some patterns like this, okay, and I believe convolution neural network can properly classify it. So we can build a model. For example, that's a very simple model. That is simply just a dense model. Flatten means we like to represent this data without two dimension. We only use one dimension to represent this data, so that is the function of flatten. So we use a dense function right here. So since this is the homework you already you have finished before, so basically if it were me to do such kind of homework, I will use some convolution neural network or some max pooling and some dense functions, try to create my own network, which would be, I think, would be more helpful to do such kind of modeling. Okay, and of course you can change your activation function. You can change your number of neurons in your neural network. It depends on you. But at last we have 11 class, so we have a class right here, and of course we have several different loss function you can use because it is a classification problem. So I use cross entropy. Okay, because it has only one class. Okay, for each data point, okay, it has only one class, so it will be 1, 1, and multiple zeros. So I use the sparse categorical cross entropy. Okay, so let's do the loss function I choose. Okay, and the optimizer I choose the basic one, which is SGD. So I believe the result is not that good. Okay, so the epoch right here is 5. So we can see that is the epoch we trained right here, and I believe the result is not good. I believe, where is the result? Right here. The accuracy of classify those 365 samples. If we do some tenfold classification, okay, we have tenfold classification. The result is only 22% of the data will be classified into the correct categories. Okay, but that is the data I provide to you. As I mentioned before, in my version, okay, I changed those data, those structure to convolution neural network. Okay, you can simply just use the neural network used in digital handwriting example. Okay, it has two set of convolution and max pooling, right? And it has a very large softmax that you can use this structure, okay, which will provide you a better performance. And I deliberately use a very basic optimizer right here, which is SGD. But basically, if you use Atom or some ADA, some other more advanced optimizer, I believe the accuracy will much better. Okay, and even though you can use some other loss function, which is good. Okay, which is good. We can use sparse. I believe you have answered those things, so I think you have already checked out the those function in Keras. Okay, so I think the model right here, I believe the accuracy should be higher than 80%. No matter how you change your network, okay, because this model I use right here, the epoch has very little. It should be larger than 5. Okay, the SGD is not good, and the sequential stack is not good. If you change them, okay, to a convolution neural network, you change the optimizer, you change the number of the epoch you want to use to do the training, I think the accuracy should be higher than 80% or even 85, even 90%. Okay, and I hope your model will not overfit. Okay, but we will talk about this by using another slide. Okay, we stop right here. It is 10:04. Okay, so we take a break. So please come back at 15 after 10. Okay, 15 after 10. We will discuss some problem about overfit. Okay, so that's it.